So we have the measurement problem in quantum mechanics. Standard quantum mechanics doesn't define when wave function collapse occurs, but we really need to know when it occurs in order to make predictions properly. And wave function collapse can't just be an emergent property of the Schrodinger equation. So it does seem to be like a separate thing that happens, and we don't know when. So there are a few possible fixes, and the most common one, by far the most common in the entire world, is to not think about it whatsoever. And the reason people cannot think about it is they might not be physicists. Or they might be physicists, but they're not dealing with quantum mechanics. Or they might be dealing with quantum mechanics, but they might not be dealing with systems where you're deliberately trying to control the quantum state to the kind of level where it's really hard to tell whether what you're doing should be a measurement or not, whether it should be defined that way or not. But when we are dealing with quantum information systems or interesting things in quantum computing or quantum communications, we're often riding the boundary. We're deliberately making quantum effects large, which means we're often really worried about the quantum classical transition, especially if there really are classical processes around. Another option is to really have quantum and classical objects. In other words, maybe you get wave function collapse when a quantum thing interacts with a classical thing. Then, of course, you have the obvious problem that you have to define what a classical thing is. Is a computer a classical thing? Well, it's made up of lots of little electrons, and they're clearly quantum mechanical things. It's made up of other quantum mechanical things. How many things does it take for it to become classical? How well connected do they have to be? If I start spreading them out further and further, do they suddenly turn quantum? So the quantum classical transition has to be completely defined if you're going to decide that it's a real thing. The next option is to have the Schrodinger equation as evolution and also have a separate process, which is wave function collapse, only this time go to the trouble of actually defining when it happens. Properly defined means an alien could tell when it's going to happen. They don't have to know whether you built this thing to be a measurement device or an entangler. There is actually an extra option, which is to not have this wave function collapse process at all. And then, of course, the onus is to explain why it looks like there is wave function collapse. Now, probably the most satisfying method of having classical objects in the universe is to decide that the whole quantum theory itself is only an approximation. It's just like the thermodynamics to the true theory underneath, that might be something like the kinetic theory. And this was most famously explored in the paper by Einstein, Podolsky, and Rosen, where they examined the idea of having two objects that split apart. And if they split apart and they had very little spread in initial position and momentum, then after a while their position will be equal and opposite, and their momentum will be equal and opposite. And if you measure the position of the left-hand one, then you should be able to infer the position of the right-hand one. And conversely, if you measure the momentum of the right-hand one, you should be able to infer the momentum of the left-hand one. And so because we can remove these things so far apart in space that our measurements can happen in such a time that there's no way these two things can affect one another, then the measurement on one side and the measurement on the other side shouldn't affect one another, and we should be able to learn, therefore, both the position and momentum of each side, of each particle, perfectly. Now that, of course, violates the Heisenberg uncertainty principle, and this is known as the EPR paradox. And classical quantum mechanics explains it by saying, well, the wave function collapse is non-local. But because the E in EPR was Einstein, you can see that the non-local argument was immediately disregarded. And this EPR paradox was used as evidence that quantum mechanics was incomplete. So it wasn't trying to say that quantum mechanics was wrong, because obviously quantum mechanics produces some of the best predictions that we've ever had. It's been incredibly well verified by experiment. But it does tend to suggest that quantum mechanics was not complete theory. So the idea was that the wave function was allowed to behave oddly because it wasn't really what was going on. Really, these particles that we took a large distance apart really did have particular values for position and particular values for momentum, and the measurements were just discovering what they were. And quantum mechanics and the wave function were really just calculational tools that we could use to describe statistically what we'd expect to see. So not what was actually there, but just statistically what we'd expect. And in other words, this paper was describing that there was some theory we didn't know yet that actually had all the hidden variables that we can't see in quantum mechanics, all the possible results of measurements. And for that reason, these kinds of theories are called hidden variable theories. And in hidden variable theories, reality is typically local, and wave function collapse is just learning about properties that really pre-existed. And this idea more or less dominated the field of fundamental quantum mechanics for 2 decades until John Bell came along with his famous theorem. What Bell's theorem tells us is that the predictions of quantum mechanics are incompatible with any local hidden variable theory. That's a little bit subtle to prove, but a more modern version of Bell's theorem can be explained rather simply. Let's consider the state which is popularized by Greenberger, Horn, and Zeilinger, also known as the GHZ state. So this is a maximally entangled state of three spin-half particles, A, B, and C. And we've identified the states here by the eigenstates of sigma z. So they've got eigenvalues of -1 and +1. And we've got all three of them with eigenvalue -1 plus all three of them with eigenvalue +1. Now we're going to examine what we get when we measure the following observable, which involves a joint measurement of particles A, B, and C, and we're measuring the y projection of A, the y projection of B, and the x projection of C, and we look at that joint measurement. Now in order to calculate what we're going to get when we do that, we're going to have to transform into that basis, and so we need the following relations. So in order to see what we're going to get when we measure our observable, we're going to need to transform particle A into the y basis, particle B into the y basis, and particle C into the x basis. And we're going to get a whole bunch of terms, and many of them are going to cancel, and what we're going to be left with is this. And what we notice when we look at that is that applying this observable to this state, we're actually going to get an eigenstate. We're going to get that state back. And the eigenvalue we're going to get is fairly obvious. From the sigma y operator here, we're going to get a 1. And from the sigma y operator there, we're going to get a 1. And from the sigma x operator there, we're going to get a -1. And when we multiply the three of those together, we're going to get -1. Same there, we'll get a -1. Same there, we'll get a -1. And same there, we'll get a -1. So this GHZ state is an eigenstate of this observable with eigenvalue -1. So every time we make a measurement of that observable, we're going to get the result -1. So when we multiply the spin projections of these three things, we're going to get -1. Let's think about what that would look like experimentally. You'd find some method of producing these states, these GHZ states, and you'd probably separate out your three spin-half particles, and then you'd measure them. And particle A is going to be offered its own apparatus, and when you measure this variable, you'll get a number, +1 or -1, and that'll be the measurement of its spin projection in the y direction. And often a different apparatus, you would get YB, and in a different apparatus, you get XC. And only when you brought those things together would you multiply them, and you would find that no matter what they came up individually, they'd always turn out to be -1 when you multiply them together. Now, of course, there was nothing particularly special about which one of those particles we put into the x basis, so if we redo that calculation for putting a different one into the x basis, we'll get the same answer. So by symmetry, we'll have the following result. Okay, now if we're talking about a local realist theory, then these measurements can't affect one another. And furthermore, the values that we get as a result of these measurements are not being created by the measurements, they're being discovered. So in other words, there were actual values for YA and XC and so forth, and our measurement was finding those out. And what a local realist theory means, therefore, is that these three relationships must be simultaneously true. And that means we can multiply them together. And because we know that YA must be plus or -1, then when we square it, we have to get 1. And the same for YB and the same for YC. We have the very simple result. So assuming a local realist theory, that means that if we know the product of y, and x in each case, then we can figure out what the product of x, and x would be. And what that means is if we were to measure the spin projection in the x direction and multiply those three results together, we should get -1. However, the punchline, of course, is that if we put this original GHZ state into the x basis, then what we get is this result is indeed an eigenstate of the operator, but it's got the wrong eigenvalue. We're going to get 1, -1, -1, and we multiply those together, we're going to get 1, and 1, and 1, and 1. So in other words, we're going to get exactly the wrong result. Multiplying those three values together, we're always going to get 1 instead of always getting -1. And what that's telling us is that this local realism assumption that we made in here is actually contradicting the predictions we're going to get from quantum mechanics. Because in quantum mechanics, measurements of entangled systems are contextual. In other words, you need to know not just what measurement you're making on your part of the system, but you also need to know what measurements other people are making on other parts of the system in order to know what you're going to get. And so it's inherently non-local in that sense. So Bell's theorem and its friends are really making us run out of options for solving the measurement problem. We need to know how this wave function collapse really happens, but we can't say that the wave function isn't a real thing. We can't say that really it's just a statistical description of things that are really there, because theories that we have things really there in a local sense are not compatible with quantum mechanics. And so the predictions that quantum mechanics keeps getting right, any theory like that gets wrong. And that gives us two final options. The first is to actually have a wave function collapse, but make it properly defined and make it somehow relativistically safe. And finally, we have an option where we get rid of wave function collapse entirely.